we're now moving on to the next big theorem called the Fourier inversion theorem. So this is actually just come from the classical harmonic analysis. So if you have a function inside the L1 of the unit circle, in the classical harmonic analysis, you define this Fourier transform basically is these Fourier coefficients. You treat it as a function on the integer to the complex. Okay, so now we know the set of integers is essentially just the dual group of this unit circle. But this one is actually, you can go both ways for if your function is nice enough. Okay, so if your function is nice, well, there are many conditions on what kind of functions are nice. But if your function is nice, then just starting from a Fourier transform, so starting from your Fourier coefficient, you can recover your original function by adding a bunch of summation. Okay, you basically you can treat it as integrate against some measure on this set of integers. All right, so that's kind of the idea. So we saw that many of these classical results can be extended to locally compact abelian group, and this is exactly what we're trying to do in this lecture. So we're going to prove a Fourier inversion theorem for any locally compact abelian group. So basically, we need to say what are these nice functions that allow us to do this inverse kind of Fourier transform. You go from the Fourier coefficient back to your function. So let's just recall some notations we had. So suppose I have a measure on this m of g hat, and we define this something looks like an inverse Fourier transform. So the Fourier transform is that you start with some measure, and you define it on the dual space, basically the measure on, well, you define it as a function on the dual group of your g hat. Okay, but we actually define another function which looks like something called the inverse Fourier transform. So you define it for every g, x inside g, you define it as the integral of, you integrate this x against this mu. Okay, so this mu is a measure on the g hat, so mu of the character phi, and you integrate on this g hat. Okay, so this function is a function from g to the complex. So it looks like some way of transforming from the Fourier transform back to your functions. Okay, so that's why it's often called the inverse Fourier transform. And one thing you may notice is that this phi of mu for each of these mu is actually an L infinity function. That's kind of trivial because when you do the absolute value of that, that's going to be less than or equal to integrate, because each of these phi x is a character. So you integrate 1d mu, but mu is a random measure on the g hat finite. So you have a mu that is bounded above by its norm, right? So what we have is that this phi of mu is inside the L infinity of g. Okay, so they're not just some random unbounded function, but they're actually in L infinity. Well, if you recall when we talk about the Buchner's theorem, so the Buchner's theorem basically says the following. So if you have a mu which is greater than or equal to 0, then what you can have is that this phi of mu is going to be, while you're integrating a bunch of these characters, they're all positive definite, and you integrate along some positive measure. So this is going to be positive definite. And the Buchner's theorem tells you the converse. Okay, so if you have some function that's positive definite, so you actually come from something that's greater than or equal to 0. Well, so now if I just now consider all these mu, not just positive ones. Okay, so let's give it a name. So let's call it the B of g. So B of g is going to be all these kind of the inverse Fourier transform. Okay, the phi of mu, where mu is a finite random measure on the g hat. Okay, so we know that's a subspace of the L infinity of g. And moreover, we know that the positive function, the set of positive functions, is also in there. And because each of these mu, you can use the Jordan decomposition. So use Jordan decomposition. You have each of mu, you can decompose it as some positive measure, let's say mu1 minus mu2, because it may be complex, let's say mu3 minus mu4. But each of these mu I are going to be positive, so each of these mu I positive. And if you just evaluate this whole thing, this phi of mu, you can see it's also equals to the corresponding phi of the combinations of these positive phi of mu's. Okay, so let me just write it like that. Okay, so phi of mu2, and then you plus I times the corresponding phi of mu3 minus phi of mu4. So each of these phi of mu I, because mu is positive, so by Bachner, or the easier direction of the Bachner, so that's actually inside the positive functions of this G. So immediately you can see that this B of G is just essentially the linear span of all the positive definite functions. So we have B of G is equals to the span of the positive definite functions on G. All right. All right, so let's also give one more notation. Let's say we call B1 of G is just all those B of G that happens to be in L1 as well. So let's intersect L1 of G. Okay, so just a notation. And so one thing is that if your function is inside B of G, so let's say if your function f inside B of G, basically, well, f needs to be an integral against some kind of measure on the G hat. So we let this measure to be mu f. Okay, so let mu f to denote the measure, the measure in m of G hat, so that your f of x is equals to this integral. Okay, so let me just write the integral out because we're going to use that a lot. Okay, so you're integrating this phi of x d of mu f of phi. Okay, so that's our notation. Okay, so this f, you can think about a function in B of G correspond to some measure on the m of G hat. Okay, so the idea is that these functions in B of G or B1 of G are the nice functions. Okay, so their Fourier transform kind of recovers the function. Okay, that's essentially the first Fourier inversion theorem we're going to prove. But before we do that, and actually before we state the main theorem, let me just in this video go over two technical lemmas. Okay, so the proof is rather technical, and we need to prepare a little bit. So let's just bear with me a little bit. We may not know why, but we'll see what happens in the next video. Okay. So in the first lemma, so let's do the following. So if I have two functions, say f and g, inside B1 of g, okay, well, then what I can do is that because f and g, they're in B1, so I can consider their Fourier transform, so I can consider f hat, and that's going to give me a function on the dual space, and I can multiply the mu of the g, okay, the mu of g. So that gives me some measure on the m of g hat. Okay, so that's going to live inside m of g hat. I'm going to claim that this is actually equals to the g hat d of mu f. Okay, so that's the claim. Well, the proof is the following. So first of all, if I want to show two measures on the m of g hat are the same, then we can think about this m of g hat as the, well, by the Lee's representation, this is the dual space of the C0 functions on the g hat, okay, the dual space of that. And inside C0, we know from just the Fourier transform, the Fourier transform of all the L1 functions, they are a subalgebra of the C0, and they're actually a dense subalgebra, so it actually contains the Fourier transform of the L1 of G, okay, and they're due. And we know the Fourier transform of the L1 of G is going to be dense inside the C0. So because of that, if I want to show two measures on m of g hat are the same, I just need to show that they integrate the same thing against any Fourier transform of some L1 functions, okay? So let's say for every h inside the L1 of g, okay, so let's consider, we know this g hat is going to be inside C0 of g, and all of these h hat are kind of dense. And first of all, let's just consider what's the integral of the h hat against a d mu of f. Okay, let's forget about the g for now. Let's just consider what that means. Well, what that mean? Well, let's just write it out. This is an integral on g hat, first of all. So let's just write the formula in here. So I have a d mu f of phi. And the h hat, by definition, as an integral along g. So I have the h of x, phi of x inverse, okay, or phi of x bar, dx. So that give me the h hat of the this character phi. And then I have the d mu f of this phi, all right? Well, now you probably notice this integral, if I switch the order, we have if you integrate a character against the mu f, you get basically the f back, okay? So that's how you define the mu f. So let's just do that. So if I integrate g first, so I can pull out the h of x, and I integrate against on this g hat of the, let's rewrite the phi x bar as the phi evaluate at x inverse. And then I have a d mu f of phi, all right? So this one is, well, I have a dx outside as well. And the middle part, well, this by definition is just equals to the f of x inverse, okay? That's how we define mu of f, okay? If you remember what we just defined. And so this is essentially going to equal to the integral of the, let me write it out, this is h of x, and you have f of x inverse, and then you have dx. And if you just stare at it, you realize, well, this is essentially just equals to the convolution of h and f evaluate at the identity, okay? So you have hx, and you have f of x inverse, okay? So that's the convolution at identity. So here f and h, they're both L1 functions, so the convolution is indeed defined. So now, because of that, so if now I consider the integral of, let's say, h hat evaluate against f hat d mu of g, and because we know the convolution and this Fourier transform is going to respect my convolution on the L1 space. So this one is in fact equals to f convolute with h, the whole thing, the Fourier transform of this convolution, integrate against d mu of g. And this convolution again is in L1, so whatever we just computed still applies. So this is going to equals to this convolution f with h, and then you convolute again with g, and you evaluate the identity. And now because our group is abelian, so if you recall g is abelian, the L1 of g is also abelian. So this convolution, we don't need to care which way we convolute it. So we can just swap all the order as we wish. So let's just swap the g to the left and put the f to the other side. And this is fairly simple to see. This is going to be equals to gh convolution is Fourier transform integrate against the mu f, okay, which is just equals to the integral of h hat g hat d mu f, okay? And because these h hat are dense, so we have that this f hat d mu g is just going to equals to g hat d mu f, okay? So let's finish the proof of this first one. All right, so the second lemma is even more technical actually, so just bear with me a little bit. So the second lemma is just going to show that whenever you have some compact subset on your Biot space, let's say K contained in G hat that's going to be compact, you can always pick some function that's kind of always strictly positive on this K. Okay, so there exists a f inside the compactly supported functions on G, and it's also positive. So that the following thing happens. So if I consider its Fourier transform, well, I know that's going to be greater than equal to 0. But moreover, the most important thing is I want it to be strictly greater than 0 on this compact set. Okay. All right. So how do I prove this? Well, so the proof. So let's say for every h inside CC of G. All right, so let's just pick some h so that the h hat, if I evaluate at the identity character, okay, so that's by definition, that's just equals to h of x identity on all the x are just equals to 1. So that's just integral of hx dx. Okay, let's just assume that's going to equals to 1. Okay, so h is kind of equals to 1 around 0, so it's going to be strictly greater than 0, strictly greater than some positive number around this phi of v, this identity character, right? So that's I need something that's positive, so let's do the standard construction of a positive thing inside this inside P. So one way is you conjugate two things. You conjugate H and its involution, and we showed you always get something positive. Okay, so if you let G to be equals to H convolute with the H involution, okay, so we know that we actually, when we talk about the positive definite functions, we know G is in positive definite. And moreover, if you consider the G hat, okay, so the G hat is going to equals to this this whole thing hat, but we show that the Fourier transform is a star homomorphism, okay, so it will respect the involution and convolution structure. So this one becomes the H Fourier transform, and then you multiply the H check as involution, and you do the Fourier transform. But we know the when you do the check and then the involution, well, you do the involution and then Fourier transform, that's just equals to the the conjugation of your Fourier transform. So you have H hat times the H hat bar, which is just equals to the H hat the whole thing squared. And so because of that, if you evaluate this G hat of the phi at the identity, well, this is just pretty simple because your H hat at phi of identity is equal to 1, so the norm square is still equals to 1. So you have this G hat restrict to some V that's going to be positive, okay? So let's say for some V inside, contains the identity character, open set inside this G hat. All right, so now you have something that's strictly positive. Well, now what do? Well, you fix a compact set. You have a open set on which you have something strictly positive, so you try to cover your compact set with this V, okay? So now you pick some, say, psi, let's use a psi V, that's the union of them is going to be an open cover. So there exists a finite subcover, let's say psi 1 up to psi of n, okay, inside K, so that K is contained inside this union of psi I times V, okay, so I going from 1 to n, okay, so it kind of cover your space. Well, so on each of these, you kind of now you try to translate your G hat to each of these translation of V, and you in this way you build something that's also positive. So you let your function f to be the following. So you do the summation of this psi I, and then you multiply by G. So this one is also inside P and is also compactly supported. So this is CC of G. Well, the reason is, well, why it's inside P is because your G is inside P, and each of these characters, remember this K is a subset of the G hat. So each of these psi I is actually a character. Well, so we know characters, they are positive definite, and you take a finite sum, this is also inside P. And when you have two positive things, when you multiply them, they're still positive, okay, still positive definite. All right, so now you have this function f. So if you consider these, if you do evaluate the following, so if you take every psi inside K, and you consider its Fourier transform, you multiply G, and then you do the Fourier transform, evaluate another character, okay? So by definition, this is just going to be equals to the integral of psi x G of x, okay, your Fourier transform of this function, and then you multiply by the character, take the conjugate dx. All right, but this is essentially just equals to the G hat evaluate at psi inverse of eta, all right? Well, so in other words, if you just translate, you see now your function f is just a summation of a bunch of translation of these G. Each of these translation is just going to be strictly greater than 0 on the translation of the V, okay? So this basically shows that psi G is Fourier transform, if you restrict to psi of v, that's going to be strictly greater than 0, all right? And also because your g is positive, is greater than or equal to 0, so this basically shows the f hat evaluate on each of these k is going to be strictly greater than 0. We have f hat greater than or equal to 0, that just follows from they're all positive. So f is inside P, okay? So let's finish this technical lemma.